Hey, my name is Hanan Testa. This is Lab 3, Magnetic Field from Bar Magnet. So the purpose of the experiment is to observe the relationship between distance and magnetic field, understand magnetic fields through visual representation, and measure the distance dependence of the magnetic field due to a bar magnet to find its magnetic moment. So for a brief preview of the results, when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. So the magnetic moment, or mu, was found to be 1.763 amperes meters squared, and n was found to be negative 2.84. There was one assumption made, which is that we assume that the bar magnet acts as a magnetic dipole, which is necessary for applying Biot-Savart law. So the fundamental principles of this experiment were Biot-Savart law, distance dependence formula, and linearization formula, which are shown here. So for the experiment, the system was the bar magnet and surroundings were everything else. The initial conditions was the phone has to be aligned with north and the bar magnet has to be aligned with the magnetometer. So for the procedure, first we have to download the magnetometer app and find where the phone's magnetometer sensor is located. Then we line up the phone towards north and measure the distance between the sensor and the bar magnet. Next, we found the distance of the bar magnet at varying magnetic fields on axis and graphed the linearized values by taking the natural log of each side. And as you can see, this is the graph, and these are the values that we calculated. Finally, we found the distance of the bar magnet at varying magnetic fields again, but this time it was off axis or perpendicular. Then we found magnetic field by Earth based on the provided latitude and longitude, and then we found Bx, By, and Bz using the magnetometer, and corrected By due to Earth. So observations. When the magnetometer is far away from the magnet, it was seen that it measured a near zero magnetic field in the x direction. And as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. So the position of the magnetometer does have an effect on the measured x component of the magnetic field. And we need to ensure the magnetic field of the Earth does not interfere with the readings for the magnetic field of the bar magnet. So for calculations, this was a previously shown line, which is y equals negative 2.8443x minus 14.858. And we basically put this into the distance dependence equation, where n is equal to the slope of this line, which is negative 2.844, and k is equal to 3.526, which is just e to the power of the y-intercept. Then we set Biot-Savart law and distance dependence equation equal to each other and rearrange to solve for mu using r equals 1 meter. And mu is equal to 2 pi k times r to the n times r cubed over mu naught. And mu was finally found to be 1.763 amperes meters squared. So for the computational model code, first we declared the physical constants, which in this case was just mu naught over 4 pi, which is equal to 1 times 10 to the negative 7. Then we created a cylinder that would represent the bar magnet in this experiment, and also inputted our magnetic moment that we found earlier. Next, we created a function that would calculate the magnetic field, and then we created 6 observation points. The first 2 were for on-axis, and the last 4 were for perpendicular to the axis. And for each observation point, we created an arrow that represents the magnitude and direction of it. As you can see here, we also did the same thing for the perpendicular distances, and we also inputted the average perpendicular distance into the code and printed that out. And then we created additional observation location and found the magnitude of the magnetic field there. After printing that out, we can see that the model code looks like this with all these values. And similarities between the real world and this model shown is that on-axis vectors point in the direction of mu, and perpendicular vectors point opposite of mu. However, there were some differences, which was the net B experimental was 6.451 times 10 to the negative 5, and B net theoretical was 1.659 times 10 to the negative 5, with a percent difference of 74.28%. Possible errors could have incorrectly determined where the magnetometer of the phone was, possible electronics in the room that skewed the data, and could have incorrectly recorded distances during the experiment. Computer errors could have incorrectly created the computation models on those groups. Discussion. Um, Earth's magnetic field would have interfered with the bar magnet's magnetic field, and results would have been skewed. And if we were to stick two identical magnets together, the magnetic field would be expected to be double in size, but maintain the same direction. So in conclusion, both Biot-Savart law and distance dependence can be applied to bar magnet to get fairly accurate results using computational modeling, and bar modeling can be used to accurately model magnetic dipoles. Thank you.